A protostellar cloud will continue to collapse as long as the gravitational binding energy can be eliminated. This excess energy is primarily lost through radiation. However, the collapsing cloud will eventually become opaque to its own radiation, and the energy must be removed through some other means. The dust within the cloud becomes heated to temperatures of 60, 100 K, and these particles radiate at wavelengths in the far infrared where the cloud is transparent. Thus the dust mediates the further collapse of the cloud. During the collapse, the density of the cloud increases towards the center and thus the middle region becomes optically opaque first. This occurs when the density is about 1013 G/cm3. A core region, called the first hydrostatic core, forms where the collapse is essentially halted. It continues to increase in temperature as determined by the virial theorem. The gas falling toward this opaque region collides with it and creates shock waves that further heat the core. Composite image showing young stars in and around molecular cloud C-FUSB. When the core temperature reaches about 2000 K, the thermal energy dissociates the H2 molecules. This is followed by the ionization of the hydrogen and helium atoms. These processes absorb the energy of the contraction, allowing it to continue on timescales comparable to the period of collapse at free fall velocities. After the density of infalling material has reached about 10.8 G/cm3, that material is sufficiently transparent to allow energy radiated by the protostar to escape. The combination of convection within the protostar and radiation from its exterior allow the star to contract further. This continues until the gas is hot enough for the internal pressure to support the protostar against further gravitational collapse, a state called hydrostatic equilibrium. When this accretion phase is nearly complete, the resulting object is known as a protostar. N11, part of a complex network of gas clouds and star clusters within our neighboring galaxy, the Large Magellanic Cloud. Accretion of material onto the protostar continues partially from the newly formed circumstellar disk. When the density and temperature are high enough, deuterium fusion begins, and the outward pressure of the resultant radiation slows, but does not stop, the collapse. Material comprising the cloud continues to rain onto the protostar. In this stage bipolar jets are produced called Herbig, Haro objects. This is probably the means by which excess angular momentum of the infalling material is expelled, allowing the star to continue to form. Star formation region Lupus 3. When the surrounding gas and dust envelope disperses and accretion process stops, the star is considered a pre-main sequence star, PMS star. The energy source of these objects is gravitational contraction, as opposed to hydrogen burning in main sequence stars. The PMS star follows a Hayashi track on the Hertz-Sprung, Russell, H.R. diagram. The contraction will proceed until the Hayashi limit is reached, and thereafter contraction will continue on a Kelvin-Helmholtz timescale with the temperature remaining stable. Stars with less than 0.5 m thereafter join the main sequence. For more massive PMS stars, at the end of the Hayashi track they will slowly collapse in near hydrostatic equilibrium, following the Henai track. Finally, hydrogen begins to fuse in the core of the star, and the rest of the enveloping material is cleared away. This ends the protostellar phase and begins the star's main sequence phase on the H.R. diagram. The stages of the process are well defined in stars with masses around 1 m or less. In high-mass stars, the length of the star formation process is comparable to the other timescales of their evolution, much shorter, and the process is not so well defined. The later evolution of stars are studied in stellar evolution.